Hello everyone, my name is Josef Strini and I will talk about an approximation of Gerber-Shiu functions in renewal risk models. This is a joint work with Stefan Thonhauser. First of all, I want to introduce renewal risk models. We denote by XT the reserve process of an insurance portfolio starting in X0, and C is the state-dependent premium rate, NT the renewal process with jump intensity lambda, and YI are the ID distributed random variables which correspond to the claim height. Here we can see a sample path of such a process, increasing deterministically, then we have a downward jump, and then again increasing deterministically. If the process becomes negative, then the insurance portfolio is ruined and we stop the business. Now, turning to the extended Gerber-Shiu functions, here we have g of x and t prime equals this conditional expectation. This is the extended Gerber-Shiu function for L and psi, where this here is the running reward term, and this here is the terminal reward term or penalty term, depending on the sign of psi. Of course, tau is the runtime, and here x tau minus is the reserve prior to ruin, and this term here corresponds to the deficit of ruin. And in general, there is no explicit representation of such a function, and therefore we link this function to a partial integral differential equation and use an approximation procedure to solve this equation. So we obtain an approximation for this extended Gerber-Shiu function. And on top of this, we incorporate or want to incorporate estimated characteristics, which means that we estimate the interval time density and the distribution function of the claim height y, and plug this into our approximation procedure for the PIDE solution and obtain the extended Gerber-Shiu function with where we have used real data or simulated data for the underlying quantities. Okay, first of all, we have to use a so-called Feynman-Katz formulation. We have to follow lemma. If the function h satisfies that it lies in the domain of the infinitesimal generator A, where A is the generator of the above Markov process. Of course, here I have to mention that we have to use the so-called backward Markovization technique and add an additional component to the process, the time since the last jump, such that the process becomes a Markov process. Then we have this extended process as our Markov process, and A is the generator of this process. Yes, and if this function h lies in the domain of the generator and fulfills this equation, then h can be written as this conditional expectation. And if additionally L tilde here has this special form and psi and h fulfill some other conditions, then h really is the function g, our extended Gerber-Shiu function, as in 1. On the other hand, of course, the Gerber-Shiu function g from above lies in the domain of the generator, and it fulfills this equation if L tilde has this special form. So we can really link our extended Gerber-Shiu function g to this generator equation, and now we have to solve the generator equation, of course, and we do this by an approximation procedure. We approximate the infinitesimal generator A by the generator AH, where we just use the finite differences and a finite or discretized version of the integral to approximate this infinitesimal generator. And we can show that under suitable conditions, that this difference tends to zero uniformly in X and T prime, which leads to the convergence, the reconvergence of the underlying processes. And this in turn yields the convergence of the associated extended Gerber-Shiu functions. So also the conditional expectations converge. And this means that we really can approximate the solution by approximating the solution of this PIDE. On top of that, we have, as mentioned above, we want to estimate the density and plug this estimator into the PIDE. Therefore, we use kernel estimators because they are smooth enough. So we estimate the density of the interarrival time t in order to estimate the intensity lambda. And what we obtain in the end is uniform convergence in X and uniform convergence on compacts in T prime of this difference to zero, where here, again, as above, AH is the discretized version of the infinitesimal generator, and AH hat is the same discretized version of the infinitesimal generator, but we use the estimated characteristics instead of the real distribution functions and the real intensity lambda. And as above, we obtain almost true convergence of the associated extended Gerber-Shiu function. So we really can compute our extended Gerber-Shiu function using simulated data or real data. Now we have some examples. First of all, we denote by the solution of the first approach, just solving the ODEs. We had denotes the same solution, but with estimated characteristics, and MC of X and MC hat of X denotes their Monte Carlo simulated counterpart. And in the first example, we want to compute the probability of hitting A before hitting 0. Therefore, tau 0A denotes the first exit time. Q, the function we want to compute, is just the probability that tau A, the hitting time of A, equals the first exit time of 0A. And for this set of parameters and this special state-dependent premium rate, which we have seen at the beginning for the sample path, this is just if X is close to B1, then this becomes 0, and if X is close to A1, then this again becomes 0, and A1 and B1 is 0, 0, and 10. And we want to hit the value A equal to 6, and Y and T are both gamma distributed. Then we obtain here, if we decrease the step size h, then our function, which is here the solution of the ODEs, really approaches the solution we obtain via Monte Carlo simulation here in the dashed black line. And here the hitting probability in X equals to 1. Original in black and estimated in red. Here we can see that the estimated intensity really impacts the solution of the ODE. So this procedure is quite sensitive with respect to the estimation. And on the other hand, we have a second example where we compute an extended Gerber-Shiu function for this set of parameters, where psi is e to the minus beta times z and L is equal to 2. And we use the same state-dependent premium rate as before. And here we observe that the Monte Carlo simulation is less sensitive with respect to the estimation procedure than our solution is. Since here in black, this is the solution of the ODE approach, and in red we have the solution of the ODE approach where we use estimated characteristics, and the dashed lines correspond to their Monte Carlo simulated counterparts. And of course, we can observe that the Monte Carlo simulated solution is less sensitive to the estimation procedure. which is quite interesting. Okay, thank you for watching my video, and I wish you all the best. Goodbye.